Laplace's equation for electrostatic potential. Let us now look at some other situations where this equation is valid. That also helps us in connecting the electrostatic potential with those situations and may give us some insight. The first thing I do in this case is the continuity equation. And in deriving all these relationships, I am going to make use of divergence theorem. So imagine a fluid or heat or some particles flowing. All right, so let's make different situation. Maybe there is heat. I'll make it with color. Or there are some particles going around, diffusing, right? Then what happens? What does continuity equation tell us? So in this flow, if I look at a particular volume, there is current passing through this. We defined this earlier. So let us define a current J R as equal to the amount of quantity. I am writing quantity because it could be fluid, it could be some particles, it could be some heat per unit area per unit time. And it is directional, so it also plus the direction of it. So it flows in a certain direction. So that if this is a volume, the net amount leaving the volume would be J dot ds from each surface, and if I integrate over the entire surface, entire closed surface, this is going to be equal to the amount leaving the volume. Why am I saying leaving and not entering? This is because I am taking the conventional sense S is pointing out of the volume. So if J dot ds is positive, it means things are leaving. If J dot S is negative, this means things are entering. So J and S have the same direction, then things are leaving. But this should also equal to the reduction in the amount of this quantity inside the volume per unit time, right? So let us define the density rho as the density rho at R as the density inside the small volume. Okay, this is a very small volume that I am taking. Therefore, I am going to have J at R dot ds is equal to J at R is being calculated on the surface is equal to integral d rho by dt with a minus sign because it's reduction times d the volume. By divergence theorem, this is divergence of J in the volume is equal to minus d rho by dt the volume, and this gives me integration of divergence of J plus d rho dt dv is equal to 0. Now this small volume can be taken in any different shape, any different size, right? So this is really arbitrary, and this implies del divergence of J plus d rho dt is 0. And this really comes from conservation of mass, of conservation of that quantity. This is known as continuity equation. If rho is not changing, if the density is not changing, that means everything that is coming in is also leaving. Divergence must be 0, as we learned in the case of defining divergence. In that case, divergence of the current would be 0. Let us now apply this in two different situations, and that gives you a very beautiful feeling for electrostatic cases also. One is heat flow. You have learned in your 12th grade that heat flow in one dimension, the amount of heat dq dt per unit time per unit area is actually equal to the thermal conductivity and the differential or derivative of T with respect to x. I am going to put a minus sign here because that tells you that it flows in the direction of lowering temperature. In 3D, this generalizes to that per unit area, the heat current, right? This was 1D, it's flowing in one direction, but in the 3-dimension case, heat current is, that is the heat flowing per unit area per unit time, is equal to minus k gradient of T. So let us again consider a small volume. Whatever current is flowing out, because of that, the quantity of heat or quantity of heat energy inside is lost. So if I apply del dot J is equal to minus d rho dt, this would come out to be minus, the temperature is reducing, and that means the heat flow is going some specific heat times dt over change of temperature with time, and this should be equal to divergence of, by continuity equation, k grad of T with a minus sign outside. This becomes therefore k del square T is equal to C dt dt. This is what will determine how temperature changes with time given some boundary conditions, right? So now let us, so we have derived the equation k Laplacian of T is equal to C dt by dt. Let us take a steady state situation. That means the temperature does not change with time. This could be, for example, if I take a volume and maintain the temperature on the sides. Maybe here is one temperature, here is another temperature, here is third temperature, maintain different temperatures. Then temperature inside with time does not change with time because it has stabilized. Then dt will be equal to 0 and del square T is equal to 0. That is the steady state temperature equation. Compare this with del square V equal to 0. This is the same equation. All I have done is replace V by T. Maintaining a potential on the surface is equivalent to T at boundary is equivalent to V at the boundary. That means if I either solve this, I know the solution for this. If I solve this, I know the solution for this. Okay? So this is I can call it heat diffusion equation. Now I'm going to connect it to something you know. You have learnt and you have been told that when lightning conductors that are put on buildings have a very sharp edge. And that is because near the sharp edges, the electric field becomes very large. If the electric field becomes very large, most of the charges or most of the current in the atmosphere comes here, or lightning strikes at that point and it goes to the ground directly. All right. Now let us analyze that situation here. The current of heat is proportional to grad of T. The electric field is proportional to grad of V. So whatever the relationship is between V and E is the same relationship between T and the heat flow. All right. Now if E is very, very strong near the edges and there is no other charge giving rise to, this is Laplace equation, so there is no external charge. Same must be true here. If there is no source or sink, right, then in steady state the heat flow should be proportional to grad of T. What happens to grad of V or electric field in the case of lightning conductor? It is very strong near the edges. Similarly, the heat flow should be very strong near the edges because it is proportional to grad of T. Do we see that situation in life? And you do. Next time you buy an ice cream or you have a piece of ice cream, notice how it melts from the edges. It starts melting from the edges so that you start seeing a round shape there. And that is because at the edges, grad T is the largest. And this means the heat current is largest near the edges. So this gives you a connection between the electric field and the heat flow or the potential and the temperature. Another example of this I am going to take relates to diffusion. Diffusion is where if you put some material in a fluid, it starts diffusing slowly. Or evaporation is also some kind of diffusion if you like, loosely. Then there is something called Fick's law that tells you that the diffusion current at any point is proportional to gradient of the density of the particles diffusing, or this is equal to minus some diffusion coefficient gradient of rho. All right. So if the gradient is large, then there will be more current of diffusion. If gradient is small, if gradient is 0, there will be no diffusion. Now apply continuity equation. That means del dot J, which is minus d del square rho, is equal to minus d rho dt. That is a reduction in the particles. And in steady state, when there is a constant gradient being maintained so that there is no net inflow or outflow, you should have del square rho is equal to 0. Again a Laplace equation, and the current J, which is equal to minus d grad of rho, is like equivalent to the electric field, and this rho is equivalent to the potential. So again the similar relationship, right? So again from the edges I should see a large diffusion. Do I see that? Next time you take some potato fries or something else which is fried with sharp edges. So potato fries have sharp edges, for example. They will have these edges out here. What happens in frying? Frying, water evaporates or water diffuses out because of the heat. From these equations, suppose we assume kind of a steady state, where do you expect the maximum diffusion to take place from? It will be from the edges, because that is where electric field is maximum and that is where the current of diffusion would be maximum. And you should see the edges getting brown faster, and that is indeed what happens, right? So what we try to do in this lecture is connect the Laplace equation with other known situations so that next time you see it, you get a feel for the electric field. Laplace's equation.